Okay, this lecture is going to be on the neural message passing framework. So we're going to start by giving a high-level intuition about what this is and the goals we're trying to accomplish. We'll go through the general equations of how to think about this and some particular instantiations of common architectures, and then we'll wrap up with an example of code for how to implement this. So a little bit of background here. In general, our goal was to learn an embedding of nodes, and that means we want to map nodes to coordinates in a coordinate system. And a useful embedding will allow us to do cool things like draw decision boundaries. For instance, maybe we're trying to classify fraud from not fraud in our graph, and it would be nice if we could put these nodes into a place in this coordinate system that was useful. So, for example, easy to draw this decision plane as opposed to giving them random coordinates where we'd have to draw some very complicated decision plane. So our goal in all of this is to map our nodes in a graph to coordinates, which we'll then use for downstream tasks like classification. And in particular, we want our embeddings to reflect the neighborhoods of our nodes. So, for example, if two nodes share many of the same neighbors, they should be close together in this embedding space. And that's how we're going to take advantage of the information encoded in our graph structure. So I'd like to give a motivating example that we can refer to continuously throughout this lecture so that some of these abstract concepts can be made more concrete. So in this graph, nodes represent people, and the features that we have for these nodes are just age and net worth, so a two-dimensional vector. And then the edges in this case represent whether one person is in the other person's phone contacts. And to be simple, I'm not going to have directed edges, that if either one is in the other person's contacts, they share an edge. And then the feature for our edge will be the number of phone calls in the last year. The idea being that the larger this number is, it might encode something about the strength of that relationship. And in this case, we're going to be focusing on a single node in this little subgraph, but I want to be clear that the steps we're going to talk about apply to every node in the graph. We're just going to talk about one for simplicity. Okay, so a little intuition behind what the message passing framework is doing. So again, the goal here is to calculate these neighborhood-aware embeddings for our nodes. And the way we're going to make a node aware of its neighborhoods is we're going to have all of the neighbors send messages to the node. So you see this envelope here coming along each of the edges of the neighbors of our orange node. And then we're going to use those messages to update the representation that we have of our node to be something new. And this new representation will take into account these messages as well as the previous state. So now we'll have a graph structure where the nodes have new features, not just age and net worth, but a new computed feature which says something about its neighborhood. So it's informed by the age and net worth of all of its neighbors as well. So to frame this problem, we're going to define three different functions. The first is called the message function, and its job is going to be to compute the message using the node and edge features involved. The next function will be the aggregation function, and that's going to combine the various messages into a fixed length vector that represents the entire neighborhood. And then finally, we'll have the update function, which computes a new node embedding using the aggregated messages and the old node embedding. So next, we're going to dig deeper into each one of these functions. So first, we'll start with the message function. We have m subscript ij. So this is the message that's going from node j to node I. And we can repeat this message passing step many times, and the superscript k will indicate which message passing step we're referring to. And then the message function itself, this script m, what it has available to it are the node features of I, or the current representation of I, the current representation of j, and by current I mean at step k, which is why this k is up here. And then we also have the edge features, this eij. So if we have just this pair of nodes, where hi is the one we are referencing right now, hj is one of its neighbors, and these vectors representing the various features of the edge and nodes, this message function is going to take all that information and compute some vector, which is the message, and that will be sent from J to I. Now let's talk about a couple instantiations of the message function that you'll see in the papers. The first one is simply a copy of the neighbor's features, HJ. So this would be, in our example, the age and net worth of all the neighbors being sent to our destination node. Another way you might want to do that is to take those features but then scale by a constant, where this constant is proportional to the number of degrees of node J, for example. So in this case, maybe we have an angel investor in our phone contacts who has many, many other phone contacts. So the fact that they have that many people that they talk to, we might want to divide by that number if we're trying to model something like access to capital, because they can't give all that capital to everyone they know. Another example is having an attention mechanism. So this would attend to all of the neighbors of I and look at how similar they are, for example. So by comparing the features of HI and HJ, you can come up with an attention score for how important HJ is to HI based on their features, and then that is a weight that we will apply to scale the message coming from J. So you can imagine doing this over all the neighbors, and each one gets a different weight that sum to 1, and those weights multiply the messages to scale them. So that was the message function. Now we're going to talk about the aggregation function, and that operates on the messages. So you see our MIJKs here. So these are each of the messages, and the result that we're going to get just has I. So this is going to aggregate all of the messages from the neighborhood of I. So J element of NI here. So there's going to be some aggregation scheme that collects all of the messages coming to I from all the different J's and returns a single vector here. So with the diagram, we have all these vectors coming into the orange one. We end up having 3. We apply our aggregation function, and that spits out a single vector over here that represents the entire neighborhood. So a couple properties that are important here. The first is that we need to get a fixed length representation regardless of how many neighbors we have. So whether we have 3 messages or 100 messages, the output needs to be the same, and that will be the same size as a single message. Another important property is that it needs to be permutation invariant, meaning that if I assign these arbitrary colors here, blue, green, orange, that if I plug that in, or green, orange, blue, or orange, green, blue, the answer needs to be the same, because any order that we impose while doing this calculation is arbitrary, because graphs do not have inherent order. So a couple instantiations of this that are common. The first is the sum. So we simply add up all of the messages. So in this case, that would be adding up the net worth and ages of everyone in our contact list. And if you were trying to model something like total access to capital, that might make some sense. Average is the same sort of thing, where you're summing them up, but then you're just scaling by the neighborhood size. So this might say something about your economic class, depending on the average of the people you're connected with, as opposed to trying to total up the total amount of capital. And then max would be element-wise, so the maximum net worth and the maximum age of everyone in your contacts. So that if that had to model something, for instance, like based on an individual that you know that had the most net worth, maybe that would be an appropriate aggregation function. But in all of these cases, I hope it's clear that whether you have 3 messages or 100, you're going to get the same dimensionality coming out the other side, whether you sum them or take the max. And it doesn't matter if you add 1 plus 2 or 2 plus 1, the ordering of that underneath the sum doesn't influence the results. So it's permutation invariant. Okay, so we've created the messages and we've aggregated them. And now we have this m hat that represents the aggregated messages for node I. Now we're going to do the update with the update function. So the thing we're going to update is HI, and we're going to pass that in. So that represents our current information about node I. And then mi represents our current information about its neighborhood. And then some function will update to give us a new representation of hi. So here's the diagram here. Our current representation, we have our aggregated set of messages, and then this function maps it to a new representation, which we have this k plus 1. Here's a couple examples of that. A common one is just applying a linear projection to the neighbors. So this is something like, well, the update of hi is just a linear projection of its neighbors through an activation function. Whenever this is used, they often include self-connections in the graph, so that this aggregated set of messages includes a message from hi to itself. So its own features are included in this. But they're not given any special treatment either. It's just one other message among the broader collection of the neighborhood. The second form attempts to address that by giving a special consideration to hi itself. So hi would have its own projection matrix, and then the neighborhood would have its own projection matrix, and then this is just a bias parameter here. Another way you might think about it is, instead of wanting to sum the contributions of itself with the neighborhood, maybe you just want to concatenate them and treat them totally separately. So this concatenates the current representation with the neighborhood representation, and then jointly applies a projection in nonlinearity. So let's look at graph convolutional networks and try to frame it in this message passing world and understand it from that perspective. So this would be the update equation. We have our neighborhood aggregate, and we're applying a linear projection and a nonlinearity. And this neighborhood aggregate, as mentioned before, has self-connections in the graph. So the hi node is also sending a message that's included in this aggregate. If we write out the rest of this, the aggregation function being used is just a sum, and then the message function being used is the neighbor copy that has this structural scaling. And there's different forms for how this is done, but if you just use the neighborhood size, then this total thing would look like the average. So we have the neighborhood copy, the sum aggregation, and this linear projection. And when you add that all together, you get the equation for graph convolutional networks that you might be familiar with. Okay, let's wrap up with an example for how to implement something like this in code. So this is GraphSage, and to just briefly review this in the context of message passing, we have just a copy of the neighbor features here. We have an average aggregation, which is sum, but scaled by the neighborhood size. And then for the update, they're doing the concatenation of, this is the neighborhood vector. They have hi here, so the concatenation of that, and then projected in a nonlinearity. So that looks pretty confusing, but it turns out to be pretty simple to implement if you use DGL, because DGL is really designed around the idea of message passing. So if you're familiar with PyTorch, the first thing you do is you create a class and inherit this gnn.module. And then in the initialization method, you create all of the layers that have learnable parameters in them. So the only one we have is this W for the linear projection, so we create this gnn.linear layer. And note that we have a number of input features times 2 here. And the times 2 is because we're doing this concatenation. So if we have age and net worth of our current node, and then we've aggregated the age and net worth of all of our neighbors, and concatenate those two things together, we'll now have 4 features, 2 ages and 2 net worths. Okay, down to the more interesting piece, the forward. So this is where the actual computation happens. So notice we have the graph input and h, which is the, in our example, age and net worth of every node in the graph. And the first thing they do is they copy that into the graph data structure. So this is a DGL data structure, and they're going to be doing message passing on it, and they need access to the features. So this H has a row for every node, and then a column for each of the features. And then here's where the message passing happens. So they call this update all method. And what you pass in is a definition of your message function and the definition of your aggregation function, which they call reduce function here. So for the message function, we just want a copy of the source node, J, and they have that built in here. It's function.copyU. So U represents the source node, and V represents the destination node, the orange one. So we want to copy from the source node, and the thing we want to copy is H, which is what we just added in here, and we want to call that M. And that's just an arbitrary choice. You can call it whatever you want, but you need to give it a name. And then in the reduce function, you reference that name because you need to tell it what you want to aggregate. In this case, we want to aggregate M, which is what we just created here. And then the output of that, we want to call H underscore N. And of course, the aggregation they're doing is the mean or the average. So that's this piece. So the result of this method call will be that it sends the messages and it aggregates them and it stores it in this H underscore N. So here they extract that out into the H underscore N variable. So now we have H, which represents all of the node features, and we have HN, which represents all of the neighborhood aggregates. So they concatenate those together, as is done here, and then they pass that into the linear layer, which does this matrix multiplication. So they don't actually have the activation function here. You do that to the output of this layer. But I hope this makes it clear. It's actually quite easy. If you understand that there's these three functions, this message, aggregation, and update, well, the message function is passed in here, the aggregation function is passed in here, and then your update is just the rest of the layer that you implement. I was planning to stop here, but I thought it would be a good perspective to wrap up with some limitations, because while this is a very powerful framework and describes many of the architectures that currently exist in GNNs, it's not without drawbacks. So, for example, the aggregation function we talked about. Well, different choices of that lead to different expressive powers that are possible. So if you look at these examples here, if you were to take the mean and assume that each color is a different number, well, the mean of having two nodes with the same value is going to be identical to the mean of three nodes with the same value. So there's no way for that aggregation function to be able to distinguish between these two scenarios. So if it were important for your model to be able to distinguish between having this pair of similar nodes or having three, the mean and max both would fail in distinguishing these neighborhoods. Similarly, for max, if you have one green and one red, well, either one of those are going to be max, and having multiple reds or multiple greens isn't going to change that output. So it would also fail to distinguish this case. And mean and max both fail in this other one as well, because whether you have two greens and two reds or one green and one red, the mean is going to be the same and the max will be the same. So this is a known bottleneck, and we'll dig deeper into this when we look into the expressive powers of graph neural networks. There's some interesting work that dives deep into this issue and proves things related to graph isomorphism tests. Another limitation is that if we repeat this message passing multiple times, that we experience this well-known over-smoothing problem, which basically means that as you take averages to update something, and then you take another average to update again, and another average to update again, you end up just making everything look the same. And you just smooth all of the embeddings so that they become approximately equal throughout the entire graph. So you can imagine, like, if you're blurring an image, right? If you do something like a blur, you're changing a pixel based on what the other pixels are around it. And if you were to just keep blurring and keep blurring and keep blurring, and you do that enough, you eventually get to this blob of a single color. So this happens a lot faster in the case of graph neural networks, particularly in cases where you have very well connected nodes in the graph. So for instance, if you have a hub that would make it so that any couple nodes in the graph are only a few number of hops away, so the famous 6 degrees of separation in social networks. Well, that means if you do 6 things of smoothing, you're going to basically touch every node in the graph on average for the computation. So every node would be involved in the computation of every other node. So you can see how that would get out of hand quickly. So this is a well-known problem, and there are substantial amounts of work put into overcoming that, and we will address that in a different lecture. And finally, if you want to dig a little deeper into this topic, these are 2 resources I think are useful. The first one is kind of the first paper that came out of the quantum chemistry world that talked about this neural message passing, and that's from 2017. And then a little more recently, out of the DeepMind group came this paper that talks a lot about graphs being used in learning problems in general, and they have this relational inductive biases, deep learning, and graph networks. So they developed their own framework that's very similar to message passing, but it has a few more details. And then they've used this to define what they call graph networks, as distinct from graph neural networks. And this is used to do things like the particle physics simulator stuff that I talked about on the YouTube channel. So a very interesting work that covers a lot of ground, but you'll see a lot of similarities with the message passing framework. So that's it. I hope this gives you a clearer picture for neural message passing.